Hello there and welcome to my channel on chemistry lessons. At the moment we do predominantly focus on A-level chemistry lessons and they are designed to be full lesson videos. So please make sure you subscribe and you like to make sure you don't miss out on future videos. I do aim eventually to cover the full A-level specification. If you think there are any gaps, please let me know and I'll ensure that I fill them for you. So hopefully you find it useful and good luck. So this video then, it's a full lesson. It's a full lesson on the organic topic of 3.3.3, which is halogenoalkanes, and it's the first lesson. So we're going to look at the nucleophilic substitution of halogenoalkanes. Before we do that though, we will look at the specification and we'll look at some physical and chemical properties first. So this is going to be most likely your first look at the curly arrow mechanisms, and this is something that does cause some concern for people studying organic chemistry because it feels like there are so many of them, when in reality it's quite often the same one several times. And that's the case today. Right, before we look at these mechanisms, then let's look at some rules and definitions. So it might seem a bit obvious and straightforward, but let's look through these bullet points. The functional group of a halogenoalkane, well, that's literally when you've got a halogen, just X, a halogen in place of a hydrogen in an alkane. So let's just look at, if we got ethane, that would be ethane, and that would be a haloethane. So for example, if X was chloro or chlorine, that would be chloroethane. Defining the term nucleophile, a nucleophile is a species or a substance that can donate a pair of electrons, or you can just call it an electron pair donator. A curly arrow, for example, there's a curly arrow in a mechanism. That curly arrow represents the movement of a pair of electrons. It's a pair, it's always two electrons when you see a curly arrow like that. Bond polarity of haloalkanes. So as we move down the group, you should be aware that the electronegativity decreases down the group. And it's the difference in electronegativities that determines the bond polarity. Fluorine being the most electronegative means that the bond between a C and an F is the most polar. And as we go down, the polarity decreases. There we go, trying to show that by the size of the delta. So we've got delta plus delta minus. All of those bonds are polar, but they become less polar as we go down the group. Now, bond enthalpy is different to bond polarity. The bond enthalpy, we would have defined this back in energetics topic in physical chemistry, but the bond enthalpy is the mean average energy required to break 1 mole of gaseous bonds. In other words, it's a measure of the strength of the bond. Now, this confuses people. People would assume that as you went down, and this is the wrong assumption here, people assume wrongly that as we go down the group, the bonds get stronger because it's less polar. It kind of feels logical to say the more polar this is, the more the electrons are being pulled, the weaker the bond. It's not true, okay? The bond strength actually decreases as we go down. And that's because it's not just about the polarity that's going to affect the strength of the bond. It's all to do with the size of that atom as well. Because at the end of the day, these are covalent bonds, and a covalent bond is the electrostatic attraction between a shared pair of electrons and two nuclei. Now, as we go down the group, the atoms get much bigger, which means the nucleus is much further from the shared pair of electrons and it's less strongly attracted. So as we go down the group, the bond enthalpy decreases, which means the bonds get weaker down the group. That actually makes the haloalkane more reactive as we go down that group. Let's take a brief look at some physical properties of haloalkanes then. Now, this didn't appear on the spec, but there is an expectation that from your earlier topic on bonding that you would be expected already to have the knowledge to do this. So let's just have a look now. So when it comes to the boiling point of a haloalkane, there's two things to consider. Okay, we are going to have permanent dipoles here because of this polar bond. So we're going to have a permanent dipole. So one of the forces we're going to find is a permanent dipole, which is one of our intermolecular forces. We're also going to have van der Waals forces to consider. So that's where a comparison between something of the exact same R group with an RF or an RCl. Now we've seen already that this one will be more polar, so the permanent dipole will be stronger for this one. Therefore, the boiling point of this one will be higher than the boiling point of this one. Simply because the bond is more polar, the permanent dipoles will be stronger, more energy would be needed to separate those molecules. Now, if the R group is different, then we need to start looking at van der Waals, and that's where you can use your knowledge of branched and straight chain, or might just be a bigger R group. So for example, chloromethane versus chloroethane, they both have the same dipole here. However, the ethyl, the chloroethane, has a bigger R group, which has more electrons, has a bigger MR, has more electrons. It will have stronger van der Waals forces. We could go into detail about what the van der Waals forces are, but again, you need to look at earlier videos on bonding for that. In terms of solubility, it's tempting to say that they are highly soluble because of the polar bond, which would mean they would form bonds with water. However, because of their organic chains, they are actually fairly insoluble, so they're only very, very slightly soluble, and again, that's only for very short chains. So typically they are insoluble. Okay. On to the main part then. This is the main bulk of what we're looking at here, is the nucleophilic substitution. And again, looking at the spec, it's very specific. It tells us the 3 nucleophiles that we need to be aware of. And these are the ones we need to make sure we know for our test and for our exams. We've already seen that haloalkanes or halogenoalkanes contain polar bonds. So we're going to look at each of these nucleophiles in turn, okay? And we're going to look at the mechanism for each one. First off then, NaOH. So where will we find NaOH? Most commonly is in metal hydroxide, so sodium hydroxide, potassium hydroxide, for example. And it must be aqueous conditions. Okay, so it must be in aqueous conditions. And in aqueous conditions, we will have hydroxide ions. Now actually, the negative charge, and I'm going to draw the negative charge on the other side because the negative charge is in fact on the oxygen and it has a lone pair. So now we're gearing up to show this hydroxide as a nucleophile, a lone pair of electrons, and has a negative charge on the oxygen. So I'm just going to pick a very typical haloalkane, being chloroethane. Now this is true for any haloalkane now. This could be any haloalkane. I've just picked a simple one to draw on the screen. Now what happens here is the hydroxide nucleophile, that lone pair of electrons, and I'm being very, very specific on where the curly arrow goes. There is no mistaking that my curly arrow goes from the lone pair of electrons to the carbon atom. Okay, and what happens next is the bond between the C and the Cl breaks, so it goes from the bond to the Cl. So we've got the movement of 2 pairs of electrons in this mechanism. We've got a pair of electrons moving from the O to the C, and the bond is being formed between the O and the C, and this O is effectively losing one of its electrons to the carbon because this is using both of its electrons to form the bond with carbon. So you're going to find that the negative charge has gone on the OH. So we now have our OH now bonded to that carbon. The Cl was bonded to that carbon, but we can see from this curly arrow that the pair of electrons from the bond has now gone to the Cl. So the Cl now has a negative charge and those 2 electrons. So that is our 2 products here. We've made an alcohol from a haloalkane. This mechanism, and this is now called a mechanism, we've shown the movement of electrons. This mechanism is called a nucleophilic because it involved the nucleophile, the OH minus nucleophile. Nucleophilic sorry, not nucleophile, nucleophilic substitution. It has swapped places. The OH minus has literally been substituted for the Cl minus. And an overall equation, we've got CH3, CH2, Cl plus NaOH, and it had to be aqueous, must be aqueous conditions, a little bit of heat, and we'll make CH3, CH2, OH, but we've also going to make NaCl. Notice how the sodium ions didn't appear anywhere in our mechanism. They were just spectator ions. They were just there, which is why it doesn't matter if we use potassium, sodium hydroxide. The important thing is it's a hydroxide in aqueous conditions. Very, very important. It's aqueous conditions. And then we have a nucleophilic substitution mechanism. 2 curly arrows showing the movement of electrons. Very, very specific on where you put those curly arrows. They will always go from a pair of electrons, either a lone pair, as you can see on the OH, or from the bonding pair, as you can see here. The bonding pair came from the bond. So the arrow will always start at a bond or a lone pair. And as you can see, the arrow is pointing to the C and to the Cl. Very, very clear. Okay, examiners will be fussy on this. Okay then, so let's look at the second nucleophile. It's a cyanide nucleophile. And a cyanide nucleophile is a carbon with a lone pair and a negative charge with a triple bond to a nitrogen. So that's our cyanide nucleophile. And we'll find cyanide nucleophiles, potassium cyanide, sodium cyanide. This time though, it's not aqueous, it's ethanolic. They're dissolved in alcohol or ethanol. Now let's have a look at a mechanism. Let's stick with our bromoethane. So there's bromoethane. Let's draw or show the polarity of that bond. And our nucleophile, it's the lone pair on the carbon, to the carbon with a delta plus, and then that bond breaks again. So you will recognize that actually this is absolutely identical to the previous mechanism. So this is also a nucleophilic substitution. And those eagle eyes amongst you might have realized I spelt it incorrectly on the previous slide. So nucleophilic, I managed to miss the C out for some reason. Nucleophilic, and I missed an S out of substitution. Substitution. So yes, I can spell, but for some reason on the previous slide I couldn't. So nucleophilic substitution, and again, the bromide or the halide that has been substituted comes out as a negative, as a halide. So our overall equation here would be CH3, CH2, Br plus KCN goes to CH3, CH2, Cn plus KBr. And functional group here is a nitrile. And something to look out for is the carbon chain has got longer. So this is bromoethane, is our reactant, and our product is propanitrile. So it's got 3, it's become a length of 3. So that's a nitrile and it's propanitrile, that one. Okay, let's look at the third nucleophile then. So ammonia, and this time I'll stick with the previous one, bromoethane, and ammonia has a lone pair on the nitrogen. It's a lone pair on the nitrogen. There we go. And again, this would just be dissolved in ethanol or ethanolic. So it's ethanolic ammonia. Ammonia is actually a gas. You may recall from GCSE, it's produced in the Haber process and it's a gas. However, if we dissolve it in ethanol, we can have it in solution. So again, this will be dissolved in ethanol. And ammonia has a lone pair on the nitrogen. So the first step will start to look very familiar. From the lone pair to the carbon, Br being very specific on where the arrows go from and to. Must be from the lone pair. Occasionally I'll see students do this. That's wrong, because it must come from the lone pair, not the nitrogen. It's the lone pair on the nitrogen. And what does this form? Let's have a look. Nitrogen is now here. Now I'm going to draw all of the hydrogens on this nitrogen, and I'll explain that in a moment, because this is slightly different to the previous two. The previous two were absolutely identical in every way, but what you'll have also noticed is that the previous two, the nucleophile had a negative charge as well as a lone pair. Now ammonia does not have a negative charge, which means once it's formed the bond with carbon, it's effectively losing one of the electrons, so it does lose a negative charge, and because it doesn't have a negative charge to lose, it becomes positive. So we need to show a positive charge on the nitrogen over here. And yes, we do have Br-. So this reaction has not finished. There's an extra step that's going to happen here. And what happens is another ammonia needs to step in, and it takes away one of the H pluses on the NH3. So it's going to take one of the H's, so from the lone pair to a H. It can be any of the H's as long as it's one of the three on the nitrogen. So any of those three it will take. So it's going to take that one, and therefore the bond between that N and that H breaks and goes back to the nitrogen, which gets rid of that positive charge. So we end up with NH2 at the end. So this is an amine. We've made an amine here. The functional group when you've got an NH2 to a carbon chain is an amine. And I'm going to name this one ethylamine. So what have we also been left with? We've now got NH3 has become NH4 plus and Br. So we do also make an ionic salt, ammonium bromide. So what would our overall equation look like here? It would be CH3, CH2Br plus 2 ammonias. We need 2 ammonias because one of them, the first one, acts as a nucleophile, and the second ammonia here is acting as a base. It's taking away the H plus. So we end up with our ethylamine, CH3, CH2, NH2 and NH4Br, ammonium bromide. So be careful with this one. It is a little bit different from the previous two. In terms of what we require, we would have an excess ammonia. Unfortunately, we're not quite finished there with this ammonia reaction because there's definitely an extra bit of spice. Now, I'm going to show the product that we were left with from the previous slide, which was our ethylamine. And we're all pleased with ourselves because we'd finished that mechanism. But the problem we have is once we've formed this amine, there's a lone pair on that nitrogen that is able to act as a nucleophile, just like we saw the ammonia at the start of the previous mechanism. So what can happen is we draw some more of the haloalkane, because you will have lots of haloalkane present and lots of ammonia present in your reaction mixture. You don't just have one of each molecule. So what can happen is once you've made the amine, so here's your product as the amine, instead of this happening, which is the ammonia acting as a nucleophile, what can happen is the amine product can actually go on and attack the haloalkane. So what happens there then? Well, exactly what happened when it was ammonia. The N becomes positive and bonded to the carbon. The CBr bond breaks. So I'll take my time up the top and see if you can follow what I'm doing. So I'm going to draw the amine out again. So there's just the amine drawn out again. But we now have a new bond from the nitrogen to that carbon. That's this carbon here. So what will that look like now? Well, the bromine's gone. it still has two hydrogens attached to it. So I've drawn the two hydrogens there and there. And then it's a CH3 group. So hopefully you can follow what I'm doing. So we're left with this. And as before, the Br- has left. And exactly as before, this nitrogen now has a positive charge. And just what happened before, ammonia can step in and take away one of the H's. And it has to take away one of the H's on the nitrogen, so it has to be this one or this one. Doesn't matter which one. So let me pick one. Let's go for this one. That takes that. And then the bond between that nitrogen and that hydrogen breaks and goes back to the nitrogen and gets rid of that positive charge on that nitrogen. So what are we left with? Exactly as before, NH4Br, so ammonium bromide. And this time we've got an NH with CH2CH3. And there's also a CH2CH3 on the other one. So we've literally put two ethyl groups on top of the same amine. So instead of being ethylamine, it's now diethylamine. And this is what we would call a secondary amine, because there's two carbon groups on the nitrogen. This first product we made is classed as a primary amine, because there's only one carbon attached to the nitrogen. So this is a secondary down the bottom here. Guess what else can happen though? We've got an issue again, because this secondary amine still has a lone pair of electrons on that nitrogen. So we could just repeat this again and end up with a tertiary amine where we end up with three ethyl groups. And even then it still doesn't stop at the tertiary. Once we got to the tertiary, it's still able to substitute further again and make what we'd call a quaternary ammonium. And the reason it stops at the quaternary is it stops with the positive, because it only manages to lose that positive charge when one of the hydrogens is taken away. Once it's run out of hydrogens, it's run out of options of losing that positive, so it remains positive. So let me show you what I mean. So this is our secondary amine that we made from that further substitution. That's our diethyl amine. This diethyl amine can still act as a nucleophile, and it's still able then to attack that delta plus on that carbon. So it's still able to do that further reaction or the further substitution of the lone pair on the N. So we're just following the exact same routine again, the same mechanism, the nucleophilic substitution. And again, if I try and draw out what we've done there, it starts to feel complicated, but I'm just following a very clear and logical pattern. I'm just going to draw my diethyl amine out again. I appreciate it's quite time consuming, but hopefully it's allowing you to visualize the logic in your head. So now there's a new bond being formed with this nitrogen and this carbon. The carbon has lost the bromine, it's been kicked out, bond was broken, so it's now bond to this carbon, which has a H and H, it's a CH2, and then a CH3. So we've now got three ethyl groups bonded to the same nitrogen, Br-. And as before, the nitrogen has become positive. And it still has this hydrogen here, just one hydrogen left that is able to be taken by an ammonia. Getting a bit crowded up the top here, so I'm going to put an NH3 with a lone pair. There it is. That can come along, take that H, and then that bond, exactly as you've seen in the previous two slides. Nothing different at all. So we've made ammonium bromide again. And this time we've got triethyl amine. We've made a tertiary amine, which is the three ethyl groups bonded to one nitrogen. So we've got C2H5. I'm just going to do C2H5 instead of the CH2CH3 just to speed things up. C2H5, and C2H5. There's still a lone pair here though, so we've now made a triethyl. We've made a tertiary amine. This is a tertiary amine. And as I've said, we are not finished there, because this tertiary amine can go on and act as a nucleophile and undergo further substitution. Let's take a look then. Let's see what happens. So here's our tertiary amine that we formed from the secondary amine, and that lone pair in the nitrogen is still able to act as a nucleophile and attack that delta plus carbon exactly as it has in the last 3 occasions, and the Br will leave. And let's have a look at what we're left with. We've got a nitrogen with 4 C2H5s bonded to it now. We've got 4 ethyls. I'm just showing ethyls as C2H5 to speed things up. The nitrogen will have a positive charge, and we've made the bromide. It does stop here though, because at this point now there are no hydrogens bonded to the nitrogen that in an ammonia can come and take. So it actually stops here. It actually stops as a positive charge, and this is known as a quaternary ammonium. Can't spell anymore. This is a quaternary ammonium ion, and this will actually make quaternary ammonium bromide. This is a quaternary ammonium salt, and that's where it ends. So it is far more complex, the ammonia mechanism, because you have all these possibilities. So you can often be asked, what can you do to maximize only producing the primary amine, which is that only one substitution? Now the main way you would do that is just by using a very large excess of ammonia. If you've got a very large excess of ammonia, that basically means you've got lots and lots and lots of high concentration of ammonia, which means the ammonia is far more likely to be doing the substituting other than your product. So your product won't be able to react because the ammonia is in such high concentration, it will react first. Think about collision theory. The more ammonia you've got, the more chance the ammonias have of undergoing the substitution and not the amine. It doesn't stop the primary amines from reacting, it just increases your chances of only making the primary. So yes, you will still get a mixture of products, but excess ammonia is one way of minimizing the amount of multiple substitutions. And that brings the end of the nucleophilic substitution reactions of haloalkanes. So look out for the other haloalkane lesson videos that look at the other mechanism and the ozone depletion. Good luck. Goodbye.